Okay, hello. I'm going to do a electronics project here, and I'm going to make a what I call a torque converter circuit. And it's mainly where I'm going to take a toy motor here as a prototype build for it. And it's mainly going to be that whenever the motor has a heavy load on it, that there's going to be an increase of current to it to increase torque for it. And I have the design procedures written down here, and I'm just going to take step by step and try to explain how I get all these values and the design procedures to get to the final circuit to make it work properly. So what I'm going to do is I'm going to start out now with the design formulas to make a series feedback regulator, and that's going to start first. Okay, the formulas are written right here to make a series feedback regulator, voltage regulator. I'm going to choose a current out of 500 milliamps. I choose a voltage out of 9 volts, and I choose a voltage across the motor of 6 volts. Now that voltage out is the voltage out of this transistor right here, Q1. The current out, I chose 500 milliamps, and what that's going to do is the series pass transistor, that an input voltage comes in and an output voltage comes out, and that's going to be regulated, a regulated voltage. Transistor Q2 is a feedback transistor to feed Q1, and Q8 or Q3 here is a Zener configuration. It's a transistor, an NPN transistor, connected together, collector to base, and connected backwards in the circuit to act as a Zener diode. And it can put out about 8 volts and keep it at 8 volts like a Zener diode. And so that's what I'm using here for that, for reference voltage. Okay, now it's time to solve for the resistor values of this here. So in this configuration right here, that's the configuration of a series feedback voltage regulator, series pass transistor, and these transistors here, and this Darlington pair here. And so now what I'm going to do is solve for the values here, these resistor values here now. Okay, the first value to solve for here is called IR. That's the current flowing through this resistor right here. This resistor is a pull-up resistor that connects the base of this transistor to the collector, to the supply voltage to turn this transistor on. That resistor is solved by taking the current that's going to be flowing through it. Now the current flowing through it is going to be determined by this output current here. That current, output current, is 500 milliamps. IR, the resistor current, is output current divided by 20. That would be the 500 milliamps divided by 20, which would give about 25 milliamps. Now I take the voltage, the supply voltage of 16 volts, the supply voltage, and I subtract the voltage of the output voltage plus the base emitter voltage. The output voltage is 9 volts. The base voltage would be 9.7 volts. So I take the input voltage of 16 volts, I subtract the 9.7 volts, and that would give me the voltage drop across this resistor right here of R1. I divide that voltage drop by the 25 milliamps, and that gives me about 240 ohms for R1. That is the pull-up resistor for Q1. Okay, now we're going to solve for these two resistors right here. These two resistors form a voltage divider at the base of Q2. This voltage divider has this transistor here as a pull-up resistor to turn the transistor on, and this is a pull-down resistor to put negative on the base of the transistor, to put the transistor in a linear mode. We use this transistor here as a Zener voltage, as a Zener diode of 8 volts. We add 0.7 volts base emitter voltage for Q2, and that will give us the base voltage of Q2 of about 8.7 volts. Now we want to solve for the current that's going to flow through here. A good value is to take the current that flows through this resistor now and divide that current by 2, and we'll call that divider current ID. That's about 12.5 milliamps. That's half of the 25 milliamps here. Now to solve for R2X, we take the voltage from ground to the base, which is 8.7 volts, and we subtract that voltage from the output voltage of 9 volts, and that will give us the voltage drop across R2X. We divide that voltage across there, divide that by ID of 12.5 milliamps, and that will give us a resistance value of around 24 ohms. To solve for R2 here, the pull-down resistor, we take the voltage at the base and divide that by ID of 12.5 milliamps, and that gives us about 680 ohms. And then from there we just connect Q6 and Q7 together as a Darlington pair. And what that is used for is to reduce the current that's going to flow out of the base here for this output transistor to drive. Without this transistor being in here, we have a heavier base current coming out here, and that's going to load this too much. So by putting this here transistor here in a Darlington effect, it raises the input impedance so that a smaller current flows through here, allowing a larger current to flow through here. The next resistor value is R3X. That is a series current dropping resistor. It lessens the current flowing through the motor so that we can get a 6-volt drop across here. Now, the voltage at the emitter of Q7 is a result of taking the output voltage of 9 volts and subtracting 2 base emitter voltage, Q6 and Q7, which becomes 9 volts minus 1.4, which would give us a theoretical voltage of 7.6 volts at the emitter. We take that and subtract our 6 volts across the motor that we've chosen, and that gives us the voltage drop across R3X. Now, I have chosen that I'm going to make the motor current, because I did this to some measurements and experimenting, that 50 milliamps is proper for this motor to run at. So I chose 50 milliamps for motor current. I take the voltage drop across R3X and I divide that by that 50 milliamps, and that gives me the value of around 33 ohms as a series dropping resistor in order to get to 6 volts across the motor. And that concludes that part of the design of getting the regulator, a series regulator designed and built. So now we'll do is I will breadboard this and take measurements. I'll take measurements here to make sure that we're getting 8 volts here in different places, and make sure we're getting 9 volts here and around 6 volts here. And that's coming up next.